Okay? Okay. Because of a recording difficulty, this is a repeat of the lecture that took place on Thursday, the 3rd of February. Start with some comments on assignment 5, which is now up on Sakai, having been examined and tested by one of the LAs. It's on the subject of bar strength. It's due on Thursday the 17th. In it, you will need to compute second derivatives taken with some Gaussian width sigma on an image to produce second derivative 2 tensor, and you will need to compute that at every pixel x, and do so via the frequency domain. That is to say, compute the entries to the tensor for every pixel. And for every such matrix, you will need to apply the MATLAB program Eig, and that yields eigenvectors and eigenvalues of the 2 tensor. And during this first part of the lecture, you will see why you want the eigenvalues and eigenvectors of the Hessian. But let's start with understanding what a vector is. A vector is a direction in space. In 2D, that's one vector, that's another vector. A vector has length and it has direction. We understand vectors in traditionally with respect to what I call the cardinal basis directions. Call it x and y, e sub x and e sub y. In the board, we typically would have one of the directions go horizontally and one vertically. And we would understand a particular vector, x, in terms of how much there is in the x direction, how much in the y direction. That is to say, we would represent v as v sub x, understanding v to be v sub x times e sub x plus v sub y, e sub y, or in 3D plus v sub z, e sub z. We represent the vector v by the tuple underlying v. Notice the difference between my notation. By the tuple vx, vy in 2D, or vx, vy, vz in 3D. Okay? So the point is that these tuples are with respect to a particular coordinate system. But that coordinate, and in 3D, the same thing goes. What have I done with my, here it is. In 3D, we have a cardinal coordinate system, one horizontal one, a vertical one, and a depth one. And this is EX, EY, EZ. And we can understand the vector V as so much of EX, so much of EY, and so much of EZ. But there's nothing sacred about this particular EX, EY, EZ coordinate system. This rotated coordinate system is just as good. I'll call this U1, U2, U3. There's still 3 unit orthogonal vectors each unit length, so we call it the orthonormal system. And this very same vector that was represented as some multiple of EX, EY, and EZ can now be represented as a different multiple of U1, U2, and U3. The main point then is that if you do that, you get new coefficients of the new coordinate system. And so I will call this new representation in U1, U2, U3 V tilde underline. And it's also a duple in 2D or a triple in 3D. And then also representations of the very same vector as you represented up here in the cardinal coordinate system, in the EX, EY, EZ coordinate system. And yet the tuples are different, right? The coefficients of the new basis, U1, U2, U3, is different than the one for the other basis, the cardinal basis. Okay. Now, we go on to linear operators. A linear operator is, let me put this down. A linear operator is something that takes any input vector v and maps it to some other vector a of v. Some other vector it maps to its image under the operator a. And in the E1, E2, and in 3D, E3 coordinates, this operator is applied by a matrix multiplication. Matrix multiplication implement linear operators, but with respect to a particular basis coordinate system. So capital A applied to V, V underline, in the EX, EY, EZ coordinate system is maps V into AV, where A is a matrix and V is a column vector. But this is a basic mapping of vectors into vectors that also can be expressed in the other coordinate system, the U1, U2, U3 coordinate system, which is a rotated coordinate system from EX, EY, EZ. And so we need, likewise, a new matrix, A tilde, to be applied to the V tilde so that it produces A tilde times V tilde, which is the very same vector as AV was, but different numbers. In other words, the vector in the new representation, U1, U2, U3. Okay? Now, it turns out that for every symmetric matrix, capital A, there exists a rotated coordinate system, U1, U2, U3, such that the A tilde is diagonal. That is to say, its off-diagonal elements are 0, meaning it applies each one of the basis vectors in that particular rotated coordinate system, the ith one, into a multiple times itself with no components in the other UJs. So A U1 is lambda 1 U1, A U2 is lambda 1 U2, and A U3 in 3D is lambda 3 U3. Okay? And so this particular coordinate system, the UIs that diagonalize capital A, are called the eigenvectors of capital A, and they are have associated eigenvalues lambda I. And those eigenvectors are unit orthogonal vectors. They form a rotated coordinate system, a new coordinate system, so that in your original coordinate system, capital A is a symmetric matrix, but not diagonal. It has it may well have non-zero values off the diagonal, but in this new coordinate system, there's no crosstalk in the application of the operator A. Okay, in the assignment, you're going to need to talk about the Hessian. And the Hessian is a two-tensor, it's a matrix at any given x. And you can understand it as an operator too, in the sense that you give it two directions, W1 and W2, two vectors, and it yields the second directional derivative of I in the W1, W2 direction pair. Okay. And notice that this Hessian is symmetric. And so we can rotate its XYZ coordinate system, or in 2D XY coordinate system, to diagonalize it and to determine its eigenvectors and eigenvalues. And that means that the rotated D2 is diagonal. So it has in 3D 3 eigenvalues and 2D 2 eigenvalues. And those eigenvalues are still just ordinary second derivatives, unmixed, because all the off-diagonal elements are 0. And so you get, in 3D, second derivative twice in the first eigenvector direction, second derivative twice in the second eigenvector direction. In 3D, these are all second derivatives. Second derivative twice in the U3 direction. Correct me if I make a typo, please. And this is completely consistent, and of course that will yield also the eigenvectors U1, U2, and U3 as a result of that diagonalization. Okay, now, why is this interesting with regard to bar strength? Consider a dark bar on a light background. So I've drawn this down here. This is supposed to be an image. So we can take second derivatives in twice in the same direction in any direction we want. Where's my vector? Go. So we can take derivative this way, this way, this way. It turns out that the maximum over all second derivatives of all second derivative directions of second derivatives takes place in an eigenvector direction of the Hessian. Okay, what you're doing is you have a kernel which looks like looks like this in cross-section. It's a dark bar with a little bit of side lobes. And that matches this bar in this direction best. Whereas in some other place, this same directional derivative wants to be taken across the bar that way. And those are produced in the eigenvector directions. And the eigenvalue that you get out of those, which are respectively the max over all directions of d2ww, max over all w, those directions are, those eigendirections will give you two eigenvalues in 2D, one of which is larger than the other typically. You'll have a maximum of the two and a minimum of two. It's possible the two are equal, but that's a special case that I'm not worried about right now. And the maximum of that will give the bar strength at the position center of the bar that is stronger if this width matches this width. And that's what you're after in assignment 5. Okay? Since this is a repeat of the lecture, there won't be questions, but I got questions in the regular class of this. Okay, so I'm going to now erase the board and continue on with the slides from the lecture. So let me go ahead and erase. I can find an eraser. All right. There was one topic, and I wanted to talk about with regard to convolution. That is to say, the implementation of shift invariant linear operators. And that is, it can be interpreted input by input or output by output. So consider the delta input for this shift invariant operator, let's say T. And so T on this delta input, and I remind you the delta input is simply, in discrete terms, it's just at 0, a spike of unit intensity, and 0 everywhere else. And according to the formula for if H is the kernel associated with X, the application of H to the delta function centered at Y is that formula, which is just H of Y. The delta function is 0 at every y except for x equals y, where it's delta 0, and then it pulls out the value here. So what that means is that if you have an input of a delta function, you have an output, which is whatever the kernel value is. Okay? That's why the kernel, is also called the impulse response function. The delta image is an impulse at 0, and it produces a response of h of x. So that's fine. But now consider what happens when you have an input which is some image values. Well, this can be understood as this much times an impulse here, plus this much times an impulse here, plus this much times an impulse here. So I of x equals sum over I of x sub I times delta of x minus x sub I. Right? And as a result of the linearity of t of I, t applied to I, if you will, is sum I, we're going to call this I sub I h of x minus xi. Because t of delta of x minus xi is h of x minus xi, according to what I've just told you over here. What that means is that you're replacing each I sub I by its by I sub I times the corresponding impulse response function centered at xi. So in other words, this impulse, which goes up to here, is replaced by this guy over here, which is larger, is replaced by the same impulse response function, but centered at it, and multiplied, and its height is the height I sub I, which is, of course, different. And then all these different red functions are added up. They're superimposed to produce the overall result. So this is an interpretation of convolution, input by input. The interpretation is that every intensity value in the image is replaced. Okay, we've got a 2D image. Let me get something darker here. A 2D image. And here's an impulse, 1 in that pixel and 0 everywhere else. And it's replaced by h centered at the same place. Okay, so there's some intensity values at various positions, little h. And this guy is replaced by its intensity times this, in the original image, times this impulse response, whereas the intensity over here is replaced by its corresponding impulse response function multiplied by its value. And all these guys are added up over all the image, superimposed. Okay? So this is the input by input interpretation of convolution. Now we're going to go on to just think of output by output. And by output, we want to look at all the results in the output position by position and ask what is the weight of each of the input positions that correspond that have an effect on that output position, right? And basically the math that I show here on the screen, I'll just not this green, but where is it? Yeah. It shows that the output by output interpretation says that the weighting function on I, not the weighting function, but the contribution function of I. So now we're talking about an output position here. And want to know what the contributions are of the weights, of the intensities, on the intensities around it to that guy are. And what this says is that it's h of minus z. That is to say, if you had a symmetric, okay, so here's h and here's x in one dimension. If you had a symmetric impulse response function, and by the way, need not be positive only, then its reflection simply takes this h of x to h of minus x and h of minus x to h of x. But since this is symmetric, it doesn't change things. But if, on the other hand, I had an impulse response function that was not symmetric, then its reflection would be, need another color, would be, if it was wider on the right, now it's wider on the left, right? And in 2D, what that means is you have to reflect not only, this is an image, so now this is x and this is y, it means you have to, backwards of course, x and y, although it doesn't matter what I call them. You have to reflect in x and reflect in y, about the origin. Okay? So, this is the output by output interpretation. Every output value is affected by the input values according to the contribution h of minus x, underlined. Let's apply this idea to the comb function. We're going to need the comb function for understanding the relation of a discrete image to its corresponding continuous image. And the comb function ends up being multiplied by the comb function at the spacing of these pixels. Okay, strictly the brush function in 2D, but I'm going to think of it in 1D. And so we have these offset delta functions with every one of these impulses, delta functions, separated by delta x, the same delta x. And according to what I've just said in regard to impulse response, what we're going to get out is replacing this guy by the impulse response function, this guy by the impulse response function centered at it, this guy by the impulse response function centered at it, and so on all the way down the line. And all these results added up, which is going to produce some sort of a function like so. And we will see why we want to have delta x times the Cohn function. But we're going to be then therefore interested in the transfer function corresponding to this sampling. Okay. With the h corresponding to averaging over the pixel, which will typically be done by a rect. Another convolution kernel that we're going to be interested in has to do with the imaging process itself. In imaging, you start out with an image, I'll call it S of x. It's a scene. You know, I take a picture of this whole room, and the scene is all the intensities that are being sent from all of y'all to me, who hold the camera. Okay? But cameras don't just transmit faithfully. They have an aperture too. They apply a kernel. At least the better ones do. There exist nonlinear ones that do some kinds of distortion, for example, but let's not worry about those for now. We'll cover those later in the course. But the ones that are linear can be understood to apply some kernel h of x to produce the actual image. And so we're interested in knowing what h of x is because, for example, if we want to de-blur and get back from I 2s, which is possible if there's a completely noise-free image, we're going to need to know what blurring function was applied by the camera. And what I just said is that h is simply the application of the convolution to the delta function, the so-called point at zero. And so this particular camera is represented by a so-called point spread function. It's just the convolution kernel that it's applying. You make an image. You put one bright spot of unit height there. You take a picture of it, and you look at that picture. I mean, you put that picture result into the computer, and that is h. Okay, so same idea. This input produces h. We can also do this to lines rather than points. We get something called the line spread function. And from it, you can compute the impulse response, the point spread function, but I'm not going to get into that here. Okay, so we have all these functions, all these convolution kernels that we're going to be interested in applying. But of course, computationally, I've made the argument that when you apply a kernel, you'd rather do it most often in the frequency domain because that's a much more efficient way of applying a convolution, of applying a shift invariant linear operator. It also turns out to be useful in terms of interpretation because the different sinusoids at different frequencies can be understood to capture level of detail. So a sinusoid that has a very long wavelength that goes very smoothly here, big wide wavelength, okay, is said to have capture a low level of detail, information that is smoothly varying over large regions, whereas one that goes up and down and up and down and up and down very fast is understood to have to capture small level of detail information. And for that, we need to be able to apply to understand the application as a multiplication in the frequency domain. That is to say, we need to know what the transfer function script h is so that we get in frequency domain S of nu applied via multiplication with the Fourier transform of h, and that's times, not involved, the Fourier transform of the image. Okay, so any time we have an input and we want to apply convolution with the kernel, we also say that's equivalent to taking the Fourier transform of the input, multiplying it by the Fourier transform of the kernel, which is the transfer function. And so we want to know what the transfer functions are. And on this slide, you have all the transfer functions that you're really going to need to use in this course. And for that matter, relatively little use of others, even in your in your own applications of the ideas in this course. Okay, so what do we have here? We have a list on the left of kernels, and on the right, their corresponding transfer functions. So let's start off with the top line, the impulse response function. Okay, so the impulse response function, delta, in space looks like so, but in frequency, this is space, is the constant function 1. Wow. We think of this guy as unbelievably local. It's just 0 everywhere, except for right at x equals 0, or in 2D, x equals 0, y equals 0. But that's not what the Fourier transform says. You better be careful. It says there's an equal contribution at every frequency. And when you multiply by 1 you multiply an input by 1 everywhere, of course, that doesn't change it. You have the same output as input after you apply and that's, so all that says is that the convolution kernel delta of x is the identity operator. It leaves the input image the same, the output image is the same as the input image. And it does so by being faithful at every frequency. Okay? Now, what happens if this guy is not at 0, but is centered at some position x equals x0. Okay? And the image will be at x0, y0. Anyway, in 1D, the transform is e to the I 2 pi nu x0. Well, this function, this is the complex domain that I'm now drawing. So this is the real part, and this is the imaginary part up here. And e to the I anything is a point on the unit circle in that. We talked about that. And this position here is e to the I theta, where this is theta. So in particular, this is our theta. Notice that every point on this is along the unit circle, which is to say e to the 2 pi nu x0, magnitude is 1. So this delta function doesn't change the magnitude component, but it offsets in phase by theta. And the phase transfer depends on both x0 and is different at every nu. So you have a phase shift, a varying phase shift with frequency, but no magnitude change. Right? So a sinusoid that is like so gets shifted by some amount theta, but it doesn't change its amplitude. Magnitude is the same. Okay? So that's what happens when you apply convolution with an offset impulse. Now what about this guy here that was the cone? What's his Fourier transform? And the interesting thing is that in frequency, this guy's x, this guy's nu. In frequency, it's still a cone, but the spacing in frequency is the reciprocal of the spacing in x. Well, this is typical of transfer functions. Things that are wider in space become narrower in frequency by reciprocal. And you'll see that same thing happening in the Gaussian down here, where sigma is the width of this bell-shaped function. And it's the Gaussian, it turns out a Gaussian maps into a Gaussian, except for a constant multiplier, whose width is reciprocal to the width that you have. Wider Gaussians in space map into narrower Gaussians in frequency, and vice versa. Well, the next thing we're going to be interested in is the Rect function. It's just the local unweighted averaging function. And its Fourier transform is, let me erase some to have some room. Okay, so this is the function that in space is a box that is delta x by delta x, or delta x by delta y, but we're going to, in 1D, understand it to be this guy here, which is at delta x wide, and 1 over delta x high in order to make it be a simple averaging function. Or another way of putting it is such that the area under this is 1, and you would want the area under this guy in 2D to be 1, which would make its height 1 over delta x squared. Okay, in any case, this Rect function goes into this sine pi nu delta x over pi nu delta x. It looks like the function sine z over z with z equal to pi nu delta x. What does that function look like? Well, first of all, it has a name. This guy is called the sinc of z. It's just a name for this sine over its argument. And here we see what it looks like. It's this red function, it's sine z over z. First of all, in the limit as z goes to 0, sine z over z goes to 1. And so this function has the value 1.0 at x equals 0. And then it is the denominator, 1 over x, looks like, this goes to infinity. There we go. The denominator is this function here, and I'm going to draw its negative down here. And all that's going on is that the sine function is sort of oscillating with its ordinary frequency, but inside that envelope, the 1 over x envelope. So the amplitude of the sine sort of falls like 1 over x. And that's what we see in the slide, where this envelope here on the plus side, or down here on the negative side, falls like 1 over x. Relatively gradual fall. And this is the sinc function. And if we modify our coordinate system so that it's multiplied by pi, you get this blue function instead, because it's pi times x. You're multiplying your coordinate system by pi, your coordinate x by pi. Okay, we're going to be interested in the application of Rect and what its effect is in the frequency domain, and we'll see it corresponds to multiplying by this sinc function. And wow, notice how unfaithful this multiplication is. It takes positive weights and multiplies them by a negative weighting factor, right? The transfer function is negative at some frequencies and positive at other frequencies. That is to say, it maintains sign at some frequencies, the ones where the sinc function is positive, but at those frequencies at which it's negative, you're going to get different negative weights. If you had a positively weighted positive coefficient, it will become negative. If you had a negative coefficient at that frequency in your input, you're going to be positive, have a positive now. And it's got all this oscillations. And so we should somehow understand that the application of the rect function, we're not going to be surprised if it has, we're going to see what's called ringing in the image. That is to say, we're going to see edges in the image that get little oscillations off their edges after you apply the rect function. Okay. Basically, have two more to talk about. We talked about the Gaussian. It maps into a Gaussian. Now let's talk about taking derivatives in the frequency domain. And we're going to talk about the nth derivative. But first, let's talk about n equals 1, the first derivative operator. So this says d by dx over as a kernel becomes 2 pi nu I. Yeah. But I remind you, in our complex understanding, I is just this one in the, this is real part, this is the imaginary part. And I is just 0 plus 1I. It's put up here. And that's just I equals e to the I pi over 2. Right? It's just another way of writing I. And so we can write this guy as 2 pi e to the I pi over 2 times nu, which says that except for the multiplication by the constant 2 pi, the magnitude effect of taking a derivative in the frequency domain, first derivative, the magnitude effect is linear in nu, multiplication by nu. It enhances high frequency components on both the negative and positive frequency side, and multiplies by very low values at low frequencies. And in fact, at 0 frequency, which corresponds to constants, it negates them altogether. It doesn't negate them. It makes them go away. It ignores them. It causes them to go away. And sure enough, the first derivative of constant is 0. So that's exactly what we should expect. Right? But on top of that, this is the magnitude effect. But the phase effect is phase shift by pi over 2. Okay? So, at every frequency. Real parts become imaginary parts as a result of that phase shift. And vice versa. Okay, so far, so good for the first derivative operator. It's going to be a problem if we have bad data at some frequencies. And I've already mentioned that in real images there's noise, and although the noise level in expectation on average is the same at every frequency, typically, the image level falls with frequency because of its multiplication by its transfer function that falls with frequency, and as a result, the signal to noise is really bad, very low, at high frequencies. And if we take our derivative, things are going to be trouble because we're going to multiply by a high, the magnitude is going to be multiplied by a whole lot in high frequencies. And what that's going to mean is you're going to be amplifying the noise in the image and you're going to get garbage. And so we better not apply a straight transfer function like this, but at the high frequencies, we're going to need to make this guy fall off so that at the high frequencies, it doesn't magnify by these large numbers. We'll talk about that later when we talk about taking derivatives on real images. But in essence, what you're doing here to make it fall off is that you're also applying a Gaussian, and the product of this Gaussian and this function has the shape that I talk about, which is why I say when you do a real image, you never do it without having an aperture. You always apply a Gaussian, and essentially you're doing the derivative of a Gaussian, which in the space domain is the product of the derivative operator and the Gaussian, which is the transfer function corresponding to the original Gaussian in space. Okay, fine. What about n equals 2, second derivatives? Well, for second derivative, d2 by dx squared, we get 2 pi I nu x squared, because it's the derivative of the derivative. So we apply the transfer function multiplied by itself, which is this. And that's since I squared is minus 1, it's minus 2 pi squared nu x squared. One way to understand that is all the results are negative of the original intensity value at any given frequency in magnitude, but it's multiplied in magnitude by this function nu sub x squared. Well, I also need to multiply by the constant 2 pi squared. Again, an operator that goes really big, as in nu x gets big. And so we're going to apply our Gaussian there too. That will make this guy turn over and come down. I should have used the other color. I can't keep my pen straight. So this is going to be the actual second derivative of a Gaussian operator that we're going to apply. But this minus sign can be understood as a phase shift of pi, or it can be understood as just flipping this whole thing on its to the negative side. Either way. But this square comes into play when we consider not d2 by dx squared, but in 2d, d2 by dx squared plus d2 by dy squared. We're going to apply that to I. That is to say, we're going to get the second derivative in x plus the second derivative in twice in y, twice in x and twice in y. Or in 3D, you're going to have a d2 by dz squared. And the effect of that is going to give you a transfer function that is 2 pi minus 2 pi squared times nu sub x squared plus nu sub y squared, because all this is linear. And this thing is just circularly symmetric in x and y. Right? It's just isotropic in x and y. So this Laplacian operator is circularly symmetric, and it turns out you can show that if something is isotropic, it's circularly symmetric in x and y, or in x, y, and z in 3D, then the corresponding kernel is also isotropic, circularly symmetric, which means that you get a Laplacian of Gaussian that looks like this. Well, it's the negative of the thing that has cross sections that are second derivative operator cross sections in any direction. It's this Mexican hat operator. It's negative it's every cross section in space looks like that. It's this guy rotated around the xy axis. This is y. Okay. Okay, so if we want to take Laplacians, we're going to be multiplying in the frequency domain by the rotation of this function here about the axis. So now I need a new x and a new y, and we're going to rotate this operator. And that will be our Laplacian operation. Now it turns out the Laplacian is of interest not only as an operator to compute second derivatives, but it turns out that for edges in images turn in, which that is to say things at a high contrast, and then they drop significantly to a lower intensity. Some intensity drop to lower, or vice versa, low to high, that the result crosses zero as a result of applying the Laplacian to them. And so one way to find edges is the way you did on assignment 4, where you had delta, where you had a gradient magnitude that, or its square, that produces edge strength. But another way is to apply the Laplacian and look for places where the result is zero, is negative on one side and positive on the other side of this pixel. And so we're not going to be talking mostly about segmentations in this, but it can be either done via edge strength or via zero crossings of the Laplacian. Next, we've said that if you want to apply a kernel in space, but it may well be more efficient. As long as the kernel is appropriately wide, it will be more efficient. If you take the Fourier transform of the kernel, or know the Fourier transform of the kernel from its formula, which you have in that last slide that you saw, and evaluate at positions and frequency, and multiply by the kernel, multiply the Fourier transform of the image, and then take the inverse Fourier transform. So this gives you fast convolution for all but the narrowest of convolution kernels. It's also the case that because that multiplication operator in frequency is commutative and associative, you can see that so will the application of convolution kernels be so. We sometimes use a different word for transfer function, and it is filter. A filter is just another name for a transfer function, though typically for a transfer function that we designed, one that we want to computationally apply. We say we design a filter. This thing that I just said, we might want to design to take second derivatives of somewhat noisy images, we can call a filter. Unfortunately, the literature in common parlance misuses the word filter to describe the kernel sometimes, rather than its Fourier transform. We'll be careful in this course to use filter only to mean a transfer function, something applied in the frequency domain, but we have to realize that when you read things, you're going to see things like matched filtering, where they talk about the matched filter and they really mean the matched kernel rather than the matched transfer function. So, what filters might we be interested in? Well, you want something that lowers the effective noise in the image, which is to say decreases the amplitude in the frequency domain of the places where the noise is heaviest. And that's in the higher frequencies. So you want some kernel that falls smoothly into as you increase frequencies. And a Gaussian, we will see, is the ideal function to use from many points of view. It's a separable function. It's an isotropic function. What does that mean? Well, it means you can apply it first in x and then on the result in y, and that makes for computational efficiency. Isotropic means if you don't want to apply it in x and y, you can apply it in u sub 1 and then in u sub 2 for any two orthogonal directions. We normally think of low pass, that is to say, passing well the components, the coefficients at the low frequencies, but lowering the magnitude of the ones at high frequencies, to be done by ordinary unweighted averaging. Take a pixel and take an unweighted average of it with the pixels around it. But that's convolution with Rect, and that we've seen has this ringing artifact, and moreover, it's not isotropic. It favors what goes on in the x direction and the y direction over, for example, the diagonal directions. Okay? Or not so much favors as a different effect in different dimensions. It's biased towards the x and y directions, or alternatively biased for the diagonal directions as opposed to the horizontal and vertical directions in the image. Okay, the last one we're going to talk about in this lecture is deblurring of completely noise-free images. And then we'll say what we want to do for noisy images. So what we're saying is that our input image I of x was created by taking the scene, S of x, and convolving it with h of x, and this guy is the point spread function of the imaging device, of the camera. And we know that that corresponds in the frequency domain to taking the Fourier transform of I, its representation in the frequency domain, and multiplying the Fourier transform of the scene by the Fourier transform of H. So it's fairly clear from that what we want to do is divide both sides by H. And now, if we take this guy as a filter, 1 over H, we'll get back the scene. We've de-blurred the image. And surely that works if you have a noise-free image. Right? But H typically, if we have a positive impulse, we'll get a positive blur with our camera. Okay, so that's little h, which in frequency means this guy looks sort of Gaussian-like, and sure enough, h of x, this is little h of nu, it's the Fourier transform, which is also Gaussian-like. So it's reciprocal if this is 1, looks like that. Sure enough, if you apply that filter to a noise-free image, you multiply that, you're going to be enhancing the high frequencies because they were de-enhanced in the imaging process, and you'll be able to get a sharper image, the original scene. But we've seen that that's unrealistic because real images have noise, and so we had better turn this guy by multiplying in the frequency domain by a Gaussian. So this picture just reminds you, this guy was H. Sorry, this guy was H, and this guy was 1 over H. And we want to take our 1 over H and, okay, and then when we, in 2D, when we rotate this guy around the axis, we get what I have come to call, and some others too, a volcano filter. It has a cone, and it goes higher and higher for a while, and then it turns over and comes back down. So this is a restoration filter that will improve blurring up to some frequencies, but then where the noise gets bad, we'll stop trying to improve that and instead try to cut down the noise. So it both has a positive effect in the area where the noise is dominant and a positive effect of sharpening in the lower frequencies where the noise isn't a heavy component of the overall image. Okay, this is the end of this lecture. The next lecture is going to say a little bit about how the actual Fourier transform is computed by a very fast algorithm, the FFT, that implements the DFT, but very quickly go through that. And we're going to talk about precisely how you would do convolution, and what about applying the inverse. And we're going to want to also say a little bit about the fact that convolution in the frequency domain has this periodic effect, so that right side information pollutes the output and the left side, and the top pollutes the bottom, and vice versa. And then we're going to go on to the topic of understanding what size pixels we should have, what the sampling should be in images. Till next time.